Hi, everybody. This is Gigi from Kauai Community College. This is the fourth video in the slicing of volume series. Okay, so make sure you watch my volume by slicing number 1, 2, and 3 before you watch this one, because this is one of the harder one in the series. Okay, so let's get started here. Okay, so the problem said the region S is a circular disk, just as we see down here in the example, with the radius r. So if we think about an equation of a circle with radius r, the equation would be x squared plus y squared equals radius squared, right? So here you have x squared plus y squared equals radius squared. That's the equation of that circle. Now, the cross section is perpendicular to this circular base right here, and it stands up straight. So it pops out at you. If you think looking at the screen, it's popping out at you. And those things that are popping out at you are isosceles triangles with constant height h. Okay, so how do we think about that? I'm going to use this purple as these lines here on the circle, right? And these lines right here are the unequal side of the isosceles triangle, not the ones that are equal to each other, but the third side, right? So these are the base of that isosceles triangle, and the triangle is popping out from that base. Okay, now suppose that the height, I'm going to use blue for the height, whatever the height is that I pick for my first triangle, and I think I'm just going to pick the height to be, say, from here to here. Okay, so from here to here, that's my h. Whatever the height is that I pick, that height is going to be constant, right? Meaning it's going to be the same for all of the triangle that are standing up like that, right? So even if there are some that are like way back here, for example, that particular length, for example, like say this one right here, the height would still be the same. So that height stays constant. So h is like this, right? H is constant. And the isosceles triangle is popping out at you from here to here and here to there. And these are the equal sides, right? These are the isosceles triangle. Now, suppose we are only going to take like one slice of it. Okay, just one slice of that solid. Okay, now maybe you cannot imagine yet how it looks like, and I know I have a huge issue with three-dimensional shapes, so I went online and searched for a shape that looks kind of like this. And so here is the three-dimensional solid of that shape. The base is a circle, like down here on the bottom, right? And then these are isosceles triangles that stand up like that. So it looks kind of like a pyramid, but with a circular base. Okay, so that's the solid. And what are we going to do with that solid? We're going to take just one slice of it. So go back to my ugly picture here, but I think it does make sense to go ahead and take a look at this in this sense. Take one slice of it like this, okay, that one slice. So as you can see, that one slice right there, the thickness, we're talking about the thickness right here, right? That's being dy. So I'm just going to go ahead and draw out that one slice. The one slice looked like this. Okay, and it has a purple base like this. And then the height is blue, and it's here. That's the height. That's h, right? And how thick is it? How thick is it? It's like this thick. And how thick it is delta y. Now, in order to find the volume of this solid, I need to be able to find the volume of one slice, right? And the volume of one slice is the area of the triangle multiplied by how thick. Okay, so I need to now go find the area of one triangle. Let's take a look though where the base of this purple line come from. The purple line comes from here. It's this guy right here, right? So it's that purple line right here. Now that is the X value of the circle. You think about it right there, right? That point right there is the X value of the circle where X squared plus Y squared equals R squared. So I need to go and find out how much X is. So here, X would equal to square root of R squared minus Y squared. And the base of the triangle is 1X, 2X, right? So this right here is 2X, where X is square root of R squared minus Y squared. So this right here is 2 times square root of R squared minus Y squared. So the area of that slice is 1/2 base times height and then multiply by how thick, which is delta Y. So let's go and actually find the volume of that solid. The volume of that solid, we are going to sum up, but how are we going to sum up from where to where, right? So if we think about going from coming from the bottom here up, we're looking at from negative R to R, or better yet, let's go ahead and do the integral from 0 to R, and then from 0 to R, and then double that up because it's symmetrical, right? So it would be 2, and then from 0 to R of a bunch of slices, and the volume would be 1/2 base times height, and the base would be 2 square root of R squared minus Y squared times the height H, and then multiply by how thick, which is the dy. Okay, so we would say, let's do some cleaning up here. 2 divided by 2, that's gone, right? And H in this case is a constant, so I can pull that outside of the integral. So that would be 2H. Take the integral from 0 to R of square root of R squared minus Y squared dy. And that is the sketch of the volume and also the integral to find the volume. The question that we are going to ask you next is, look at that integral. If we know what that integral is, this right here, then we can find out the actual volume of this odd looking pyramid with circular base shape, right? So take a look at that integral and think about the picture that we drew. The integral from 0 to R, that would be from 0 to R right here, right? From 0 to R of square root of R squared minus Y squared. That's really is just these length right here. That's these x's right here. That's these length, right? Multiply by delta Y right here. Okay, so what do you call these things right here? X times delta Y, that would be the area of one of these rectangles. And we're gonna sum up a bunch of these rectangles right here from 0 to R. And when we sum up a bunch of these rectangles from 0 to R, what do we have? Area of a quarter of a circle. Look at that area, this area right here, right? A quarter of a circle. So that integral right here really is a quarter, not a half, a quarter of a circle, a quarter of a circle. Okay, and we know that the area of a circle is pi r squared, right? The radius is r, so that must be 1/4 of pi r squared. That's what that integral is, multiplied by 2h. So then the volume of that whole entire solid is reduce, you have pi r squared h divided by 2. And that's the volume of that odd looking solid. And the solid are isosceles triangle standing on top of a circular base like that. And the volume is pi r squared h. When h is the constant height for that isosceles triangle. And that is pretty awesome. We are able to find with integral the volume of very interesting looking shapes, okay? As long as we can find a volume of one slice, we can find a volume of the whole entire shape, all right? And that's the concept of volume by slicing. That is it for me.